Hello, my name is Riley Burton, and today I'm going to be talking about algebraic number theory and Fermat's last theorem. I want to kind of start my talk by introducing algebraic number theory as a subject and sort of how it came to be. And our starting point is one of the most important problems in number theory is finding integer solutions to polynomial equations with integer coefficients. These are also known as Diophantine equations. And a good question to ask from there is, how do we solve Diophantine equations? There's many methods for finding solutions, but one of the most common and powerful techniques is factoring them. And for a quick example, I want to consider the following problem. So suppose we want to find all x and y in the set of integers satisfying y squared equals x cubed plus x. Okay, and to start our solution, we can start by factoring this equation over the integers. And to do that, we kind of pull a factor of x out of this side, the right-hand side, and we will get y squared equals x times x squared plus 1. And then from here, we can notice that the greatest common divisor of x and x squared plus 1 is equal to 1. So that means that x is equal to plus or minus a perfect square, and x squared plus 1 is equal to plus or minus a perfect square. And since x squared is always going to be positive, that means we can just take the plus sign in this case. But this right here implies that x squared and x squared plus 1 are positive integer squares differing by 1. But as we know, positive integer squares differ by at least 4 minus 1, which is 3. And therefore 0, 0 is the only solution to this equation. Okay, perfect. So in this case, we were able to factor this equation over the integers and everything worked out and we were able to solve our problem. But what happens if, for example, we run into a problem like this one, which was proposed by Fermat in the 1600s, and that is to find all integers x and y that satisfy y squared equals x cubed minus 2. As we can see, neither side of this equation can be factored over the integers any further, but it was actually Euler who came along and sort of had the key idea to think, what if we imagine kind of for a minute we sort of added the square root of negative 2 to the set of integers so that we can factor it like so. Okay, and then from here we can use an argument involving the norm to show that the only common factors between y plus the square root of negative 2 and y minus the square root of negative 2 is in z adjoined root minus 2 is plus and minus 1. So this means that we can find some elements which I'll call alpha and beta in z adjoined root minus 2, so that y plus the square root of minus 2 is equal to plus or minus alpha cubed, and y minus the square root of negative 2 is equal to plus or minus beta cubed. Okay, and then we can use this fact down here to write y plus the square root of negative 2 as a plus b times the square root of negative 2 quantity cubed, where a and b now are just normal integers. If we kind of expand out this cubic term, we get this. And from here, if we kind of compare imaginary parts of y plus root minus 2 and this kind of expanded form down here, then we see that this quantity right here, 3a squared b minus 2b cubed, has to be equal to 1. And if we factor a b out of this side, we get the following. Okay, and then from here we can deduce that b is equal to plus or minus 1. We first look at the case where b equals 1, we get the following. And then from here, we can rearrange this to get a squared is equal to 1. So that means that a is equal to plus or minus 1. And now if we look at the case where b equals -1, then we get this. And this right here has no solutions. And therefore, b is equal to 1 and a is equal to plus or minus 1. That means if we kind of go back to this equation up here, we can put in our a's and b's and we get this. And here we can see that y has to be equal to plus or minus 5. And then if we kind of go and plug that back into the very original equation right here, then we will be able to deduce that x equals 3, like so. And now we can conclude that the solutions to this equation right here in the integers are x equals 3 and y equals plus or minus 5. Alright, so it turns out that this idea that Euler had to sort of extend the set of numbers we can work with in order to factor these previously unfactorable equations was a pretty good idea and is one of the fundamental ideas behind algebraic number theory. And this kind of leads me into my first definition, which is an algebraic number field. Alright, so an algebraic number field K is a subfield of the complex numbers that is a finite degree field extension of the rational numbers. And for some examples, we could have the rational numbers and adjoin the square root of 2. We could do the rational numbers and adjoin the cube root of 2. We could also do the rationals and we can adjoin multiple elements, just not infinitely many. So we could have, for example, root 2 and root 3. Or we could also even adjoin a complex number like we did in that last example. So for example, like square root of -7. And so these are all algebraic number fields. And a natural question from here, at least for number theorists, is kind of like, what do the integers look like in these sort of field extensions of Q? Or like, what is the analog of the integers in these field extensions? And that is my next definition. So we want to start off by letting K be a number field. And I wanted to note the set of algebraic integers with the capital letter A. Then the ring of integers of our number field K is denoted with this fancy looking O and is defined to be the intersection of our number field K with the algebraic integers. And to kind of help complete this analogy I was talking about earlier with like how the integers look in these field extensions, I'll draw you a little diagram. So a good way to think about this is O sub k is to the integers kind of like k is to the rational numbers. Okay, so now that we've kind of gotten these definitions out of the way, I think we're ready to begin our discussion of Fermat's last theorem. And first, I guess I'll just remind ourselves of the statement of the theorem in case anyone doesn't remember it. Okay, so just to remind you all, Fermat's last theorem says that there do not exist any positive integer solutions to the equation a to the n plus b to the n equals c to the n when n is greater than or equal to 3. And as some of you probably know, proving Fermat's last theorem is quite challenging. So challenging, in fact, that it remained unproven for over 350 years after it was first conjectured by Fermat in the 1600s. And the rest of my talk is dedicated to looking at one attempt of a proof, which was given by French mathematician Gabriel Lamé in the 1800s. In his sort of quote-unquote proof, Lemay tried to factor kind of this expression a to the n plus b to the n over a type of number field called a cyclotomic field, which is my next definition. Alright, so a cyclotomic field is a field extension of the form Q adjoin R. And here, this R is a nth root of unity, which means that R is equal to e to the 2 pi I divided by n. Okay, and then a nice fact about cyclotomic fields is that the ring of integers for Q adjoin R is just Z adjoin R. It is important to point out that in general it is not that easy to just swap the Q with the Z and then be good. This is just a special fact that happens to be true for cyclotomic fields. Okay, so before we get started, how exactly Lemay's proof is very subtle and quite easy to miss if you're not already well acquainted with algebraic number theory. So one of the nicest properties about the rational integers, or just your normal everyday integers that you're used to, is that they factor uniquely into primes. This is not true for all rings of integers in general. And so if we kind of go back to our previous problem here with Euler, this step right here, where we said that y plus 2 is equal to some alpha cubed in, or y plus root negative 2 is equal to some alpha cubed in y minus root negative 2 is equal to some beta cubed. This step actually only works because the ring Z adjoin root negative 2 is what's called a unique factorization domain, which essentially just means that its elements factor uniquely into primes. Unfortunately for Lemay, his proof resided on the assumption that Z adjoin R is a unique factorization domain, and working under this assumption, he was able to come up with a proof of Fermat's last theorem, but later on it was pointed out by another French mathematician, Joseph Liouville, that Z adjoin R in general does not have unique factorization. Okay, and now I think we're ready to get into sort of the details of Lemay's proof. So we want to start out by seeking a contradiction. We want to suppose that there do exist integers a, b, and c satisfying a to the n plus b to the n equals c to the n, and where n is greater than or equal to 3. And I won't really get into this, but it is also quick to show that we can assume in this situation that n is a prime. And so to kind of start the proof, I would like to start out with the following lemmas. None of them are really obvious at all, which I apologize for, but I'm actually working on typing up kind of the full proof, and I can just throw that into the description when I'm finished with it. So the first lemma. So I want to first recall that we can factor a to the n plus b to the n, like so, where here this R is that nth root of unity we were talking about, and Lemay showed that we can write this we can create a new factorization, which is like this. Okay, and then really quickly, before I get any further, I want to introduce kind of some notation I'll be using. So I want to denote the kth term of this factorization by m sub k, that is. Okay, and then using this, we can kind of get an alternative statement of lemma 1, where we can, instead of having this product here, we can just say a to the n plus b to the n is equal to m sub 0 times m sub 1 times m sub 2 all the way up to m sub n minus 1. Alright, and then before we do the second lemma, there's some more notation that I want to introduce. So I want to let this z sub j be equal to r to the j plus r to the minus j. R is just that root of unity. All right, and lemma 2 now. So lemma 2 has two different parts. The first one is if this z sub j divides any of these mi's, then it will divide all of them. And the second part of lemma 2 says that we can add together two of these m's, and we get some specific z sub k times a different m, which I'll call m sub l. And here, this k on the z sub k is I minus j divided by 2, and this l is I plus j divided by 2. All right, and then lastly for lemma 3, so lemma 3 says that we can kind of pull common factors out of this m0 times m1 all the way up to mn minus 1, and we can write it like so. And here, this alpha is just an element of z adjoin r, and these little m's are these big m's, the corresponding big M divided by alpha, and these little m's are all pairwise relatively prime and z adjoin r. Okay, so that's it for the lemmas, so I think we're ready to begin. And right off the bat, I want to make it clear for that this next claim, we need z adjoin r to have unique factorization. So I'll write in big red letters if z adjoin r did have unique factorization. Then we would be able to find an element in z adjoin r, which I'll call mu sub I, with mu sub I to the n being equal to one of these m sub i's. Okay, and then remembering that this little mi is equal to the big mi divided by alpha, and also lemma 2 part 2 right here. This means that we can write kind of this equation with the smaller, like reduced m's, and get this. And then from here we can find these mu elements and then rewrite this as follows. Okay, and then I'm going to go ahead and label this equation 1. And now we have two cases. The first one is that z sub k divides none of mu I, mu j, or mu l. And the other case is that it does divide one of them. So I guess let's start with the easier case, which is that it does not divide any of them. Alright, so in this case we immediately get a contradiction because that means that z sub k does not divide the left-hand side of equation 1, but it clearly does divide the right-hand side, so that's a contradiction. Alright, so that completes case 1, and so now for case 2 we want to consider the case when z sub k does divide one of mu I, mu j, or mu l. And if it does, then by lemma 2, part 1, it divides all of them. So, and now I kind of want to focus on the right-hand side of equation 1 for a minute. And I want to kind of imagine pulling all of the factors of z sub k that we can out of this mu l right here. So I want to let mu l be equal to z sub k to the power of tl times mu l bar, and mu l bar is just kind of a version of mu l with all the factors of zk pulled out. So okay, and then using this, if we kind of go back to equation 1, I want to substitute what we have here in for mu l and pull out all the factors of z sub k again that we can, and doing that we get this. Okay, so here I just substituted in this for mu sub l, and then carried the n power through both terms and then pulled out all the factors of zk that I could. And I'm going to label this equation 2. And now I want to use a combination of the three lemmas from the beginning to kind of factor the left-hand side of this equation and then pull out factors of z sub k. So starting by lemma 1, we can factor this right here like so. And from here, similar to before, I want to let this kind of fancy looking m be equal to one of the terms in this product so that we can, similar to before, write this factorization as the product as a bunch of the m's. So, okay, and then by lemma 2, we can pull out common factors of zk, and we'll get the following. And here, each of these mi bars are kind of the reduced versions of their corresponding mi's up here. So this mi bar is equal to the mi divided by zk to the ti. And then it can be shown that this whole product over here of all these mi bars is not divisible by zk. So if we kind of substitute what we have back here back into equation 2 right here, we'll arrive at a contradiction. Okay, and I'm going to go ahead and label this equation 3. And so the contradiction here is that on this side of the equation, the power on zk is divisible by n, but this one is not. This one is not divisible by n, and that sort of completes Lemay's quote-unquote proof of Fermat's last theorem. But I would like to recall that, I mean, it wasn't really a proof because this whole kind of argument at the end resided on the fact that Z adjoint R had unique factorization, which it doesn't. And unfortunately, this unique factorization problem is kind of annoying and not really immediately obvious how we would fix it. Luckily, there is a fix, and it lies in the subject of ideal theory, which will be one of the topics of my partner Chloe's talk, who's coming up next. And so yeah, I think that about wraps it up for my talk. I'd like to give special thanks to my partner Chloe for her hard work throughout the term, and also my mentor Elisa for her help with me in Chloe's project, as well as all the work she's been putting in to help organize the program as a whole. Yeah, thanks for watching. Bye.